of the equations also, not just building a high-level architecture model with classes and so on, but adding the full ability to exchange the mathematical representation. But this is very important because actually we have an opportunity now to develop into something new, at least in the European side. So, summing up, are we ready for the cyber-physical future? Now, here's what I work a lot with, and it's this wide area control. I will show you some prototypes that we have built. So you have phasor measurement units, and you have an actuator where you're sending the signals to, and you're supposed to damp the system or control the voltage or do whatever, right? So you have the process, the power system, you have sensors, PMUs, you have different sorts of controls, and then you have actuators. So this is a complete cyber-physical system, if you look at it that way. But we do not have any tools that allows us to actually model it correctly. So if you want to model the power system dynamic side, you make some assumptions on the whole IT part. And those assumptions are not a joke because, for example, you can have delays that make the system really, really bad performance. There's a way of analyzing it, but what I think is like just like as you design a car and then you tested an operator and develop, take the firmware of the new control and update it, more or less we should be able to do that in the power system today. And if you go to the power system, you can't update a controller unless you send a person there into the plant and he installs the new software firmware to the control system, for example. So we don't have the ability to really deal with this in a system engineering approach for design, simulation, and hardware deployment. So I complain a lot. What do I do about it? So this is the same picture, so I added something. We actually work on concepts, methods, and actually develop some prototype tools and following the tradition of my grandparents, the cavemen. So this is the areas that we work in. We work on monitoring tools for real time. We develop predictive tools to anticipate uncertainties. We have some control methods and technologies for design optimization and management. We have self-healing protection. And we are doing some data analytics. So basically you here have the loop of the sensor data and then the model and simulation. And somehow, not all the projects do everything, but they're somehow related. I try, it's very hard to do the Model V process, but I try as much to go through the whole process when I do projects. So one student would do the analytical part, but the next student goes and does the prototype implementation and things like that. So I try very much to use the system engineering approach. But, so we go through concepts, methods, and tools for testing operation of man-machine systems, which is basically what we're doing for power system management, and that's the goal. I would really be glad. So for the, if you're familiar with the System V process, you go from doing a conception of the concept of the tools or whatever system you're developing, requirements, then you do design and analysis, and you do implementation and testing of the prototype and so on. So to be able to do testing, you need to have a lab facility. The lab that I have built has a real-time simulator, has a bunch of PMUs and relays. And on the software side, we have data concentrators, but what is more important is that we have some toolkits where we can prototype the measurement-based applications, and we also use them to prototype the control and protection applications. So, you know, we work with the standards of stationary automation equipment. We started working with it just because I wanted to gain acceptance from the companies of what I'm doing. But actually, you know, you could just throw it away and do it everything with this configurable devices, because it's a waste of time to deal. It's very constrained what you can do with industrial equipment. But in any case, that's what we do. It looks better in that picture than this one, because as you see, it's very tiny. So this is one side of the lab, and this is the other. And it's probably, from where Jerry is sitting, is probably this area. It's bigger, it's smaller than this area here. This is really a nuke. It's one other thing is that we collaborate a lot with, I guess, some lesser known universities like in Riga and Latvia and so on, that come to train to the lab and do stuff. Another thing that we do in my lab is working a lot of European projects. This gives you some of my funding scheme, my fundings that I've gotten. It's more than 44%, it's almost 50% from European projects. This is a Norwegian funding. This is national funds. So it's 11% actually. And the funds from KTH, that's actually just for paying my salary. So it shouldn't be there, but that's how you talk about funding in Europe, so I keep it that way. At the time being, I have 20 people. This is a picture of the PhD students and postdocs in the summer. I have a technician that helps me with the lab. He doesn't actually wire too many things, but buying cables and stuff is very time consuming. He does all of that. Licenses. I have one postdoc from NC State, who's a fantastic person. 8 PhD students. Right now I have 2 master students and I have a lot of researchers. These are research engineers and master students that completed their thesis, but they just want to work for a while, or I don't have funding for PhD, so they just stay so that we can actually get things cleaned up and write papers or release the software. We have, I have 2 major EU projects. Several of my PhD projects are financed or co-financed by the Norwegian company. And I have this balance of around 85 international funding and less than 15%. The other output is publications. We can ignore that. We have now released on GitHub a modelica library for power system models, this tool that I will show you on parameter identification. And we're going to release some software development kits for Synchrophasor data, also an IEC library for data transfer. And we have built a lot of PMU applications using all of these kits. It's just taking a long time to release it because of legal issues with the company. But once we are able to release that, we can release all of the PMU applications that we have developed in my lab. Because my goal is to make all of this available so that we can progress faster. Otherwise, it's going to take really, really long time for other people to redo and relearn what we have done. I'm going to skip this because it's a lot of things. So, give you an overview of my projects. There is a STRONgrid project that I will talk about, the iTesla project. I will not talk about this project. Ideal, it's called Ideal Grid for All. It's a project on active distribution networks, and what we have done there is monitoring, control, and protection applications using PMUs in the distribution level and combination of transmission and distribution. So I can't, it's a lot of results, so I'll just keep it close to a few, but you can have the slides and go check out these links if you're interested, you have some free time. So how do we anticipate problems before operation? Does anybody know what this is?
Orville and Wilbur Wright trying to fly a plane?
Huh?
Orville and Wilbur Wright? No?
Very close. Very, very close. Amazingly close. This is a physical model to train pilots. So we forget sometimes that models have different flavors, and one of the flavors is physical models. Okay, so we do simulations from different perspectives. For trade-off studies, power electronics people do a lot of this to build fewer prototypes. Our model companies increasingly do that to avoid accidents. Nuclear power operators have to build good simulators for that. And power system people has to actually try to do this in operation, which is quite a problem because we can't really do it. And evidence that we can't really do this well is because we have so many blackouts recently. Although I'm exaggerating because there's a blackout it's a black swan, it's very hard to get it, but the fact that we get them, it means that we can't predict them. So we should be try to deal with these problems. So this is a map of the interconnection of Europe, which now includes Turkey. So I think it's soon going to be one of the biggest systems or the biggest system in the world when they interconnect the Baltic states also. And Scandinavia is connected, and the UK also, but this with asynchronous HVDC links. So this is a problem. How do you operate a system like this? So you need to be able to have a vision of right now and in the future. However, the software systems that we have developed so far have challenges because the complexity and the scale of the problem is increasing. And the complexity is because of the power electronics also that we might not be able to represent what we need to represent under certain operations. Then we actually have a lack of investments and penetration of renewables. So we need to have new tools that are able to deal with these problems that I touched upon briefly before. This picture I took myself. This is a security coordinator company, entity. They are taking care of France, Belgium, Portugal, the UK. And what they're doing is that they're doing security analysis of the power system for those countries to be able to coordinate the actions that they have to take. So you have the operator, and on top you will have these guys that are an unbiased party, more or less. That's how they're doing it in Europe. So in most security assessment tools, most take into account that it's a very few percentage that do dynamic analysis. Basically what you do is that you take some snapshots and then you go and you do some contingency screening and use a power flow model, and then you apply some faults and so on. But the computations are done a power flow model, which means that the idea is, if the idea is to predict future behavior, but there is no dynamics in the model, that means that you cannot do dynamic simulations, and that is very difficult to predict the future. So the iTesla Toolbox, the project, is actually putting a lot of dynamics into an offline tool, which is evaluating thousands of simulations using a cluster, and analyzing the output of the simulations, the time series, and extracting security indices from it. I won't show you those results, but I can give you some idea of what we're doing. And for the online platform, if you're running it and you haven't managed to make sure that nothing will happen in the future, you still have some online process that can check. And the other thing that we do is to validate dynamic models. So I will show you some of these results. This is the domain that we want to treat, this power system simulation, the time scale. In Europe, this has been a problem in the past because we have had power flows going in this direction due to bad calibration of power system stabilizers. So that's a concern from the European side. What does it mean to be unambiguous? Okay, is that we cannot be uncertain. And when you are an engineer, you have to get the correct result, not just the result. And the result should be consistent regardless of the tool that you're using. Otherwise, there's something wrong with the tool. Or is it with your procedure? How can you know that? So for that, we have developed this library using the Modelica standardized equation-based object-oriented modeling language. And we are actually using a standardized model exchange standard to use the same model within different computing environments. So this is a library that you can go download from GitHub, and something that you can see here is that we have, for example, a lot of models from different tools that have been replicated. We can deal with small models, and now we can deal with increasingly large models. So if you have ever worked with PSSC, you will know that this is the round rotor generator. So this is the exact same that PSSC has. The difference is that I know now which equations are in there, and I don't have to guess anymore for like it happened. It takes actually a bit of time because this is the model that the books give you, not the books, the manual, and then you have to go and file Richard Schultz's paper from 1978 to figure out how this should be done, which every software vendor does it in whatever way they want, the saturation. So all the nonlinearities are hard to know how they're implemented, but if you spend a lot of time and are able to implement all of these equations, then you can have the model in another platform, and that's what we did. So this is how we validate our models. One problem with power systems is because of the way that we have encapsulated the simulation and interconnected everything, is that you cannot test a controller model independently from the generator model. You have to interconnect everything into a network. So we had to set up these networks to validate each of the components. And here you have the Modelica model, the PSSC model, and a Python script to do the runs. And here you have some results. You should be doing, wow. Because if you try to get two power system software to agree, it's really hard. And actually, I can do that with my Modelica models. This is a larger model from PSSC called the Nordic 44 that I'm building. It's an equivalent grid of the Nordic system, which is matched with the market data. So we can read at the market and map all of that data into our model to represent a little bit reality. And that's what we have implemented, and we can do some simulations. And if you compare to PSSC with the same algorithm, the nice thing is that with a Modelica tool, you don't need to use the same algorithm. You can use whatever you want because the model is separated from the solver. So you can use a Runcut order 4 or a Dassault solver or a CVODE. So it doesn't matter, but to be able to compare with PSSC, we had to do the same solver, and we got very, very, very small errors that we're calibrating right now. So you can go online and get the library and get Open Modelica, and if you're interested, I will give the workshop later. Still, the companies have their models already defined in certain ways. In Europe, it uses SIM-NSOE profiles and dynamic data, proprietary dynamic data such as Eurostat. So we have built in the project with a Spanish company that did all the programming, we have built an automatic translator tool that goes and takes this different data and glues it together with the equations that we have developed for the models and interconnects them and initialize them. So here is the resulting Modelica model of the Nordic 44 starting from a PSSC file, and this is the Nordic 32 model starting from an Eurostat file. And as you can see here, we instantiate all of the models, and there we just connect all of the classes that we developed in the library. And you can look inside of the classes, you can look at the equations. If you are here later, I will show you how to do that. This is the validation against Modelica. Our mean square error is to the -4 and the -7. So we actually get same result. And this is for PSSC. Don't be fooled by these numbers. There are very small differences, you see. So we get very, very close to the -9 to the -5. And if you're using a Modelica tool, I don't have the slide, but we have tested our models and our library with 4 different Modelica tools, and you get the exact same answer. You can't do that in power systems right now. So imagine that you can go open the model in any tool, and you get the same result. That's very powerful for us now. Okay, I will skip this because... so now, assume that you have a good model. The model still has to be shared. Okay, now you share it with Modelica. Let's say you get the same answer. Still, you have to validate it so that you represent reality. And Vijay and Jerry know this very well, that if you're going to use security assessment, the quality of your result depends on the quality of the model. And this is very familiar because the quality of this model, even though it had all the right equations, the quality of the model was terrible because you can't predict the future. And I think they spent like 5 years trying to calibrate it. So this is a bad model and we want to avoid that. So we do some tools. And the idea is that you can predict that behavior. So instead, there has been so much work in power system about parameter identification and all of these things. So I decided to look at it from a different perspective. What if there are no rules on how I should do this? What if I wanted to validate the parameters of an aggregated model? Can I just identify that and validate it to get the same result? So I thought about it. What kind of tool should I have that lets me do whatever I want, formulate the problems that I want to solve, and just give me that platform? So this is the way that you can think about it, mapping in the architecture, the measurements and the models, and looking at what requirements you have. So for example, you need to support both dynamic and steady state models. You need to process the measurements with different digital signal processing techniques. You have to perform simulations of the model. You have to provide optimization facilities to calibrate the model parameters. And you have to provide user interaction. So to be able to build a tool in such way, I decided that we will use the Modelica models. But still, I wanted the Modelica model to be able to interact with digital signal processing and optimization. So what I used is the FMI standard for model exchange, which was built by the automotive community, because then you have in a card all of these different components made by different vendors. So this standards allows you to model, have a model running in different environments, and you can have different of them interconnected also. So the software that we built is called Rapid, and this is the architecture. So you go from the iTesla Toolbox, the platform, and you download a Modelica file that has everything ready for you to simulate the event and the measurements. Then you take MATLAB, and we use something called the FMI Toolbox for MATLAB that lets you run FMI compliant models, and you do parameter optimization or whatever. You solve an identification problem. You have some user interaction. This is the GUI of the software, and you can set options, settings, program of choice. How much time do I have left, gentlemen?
10 minutes.
10 minutes, so, okay. So what Rapids does is that you provide the measurements, input and output, or just just output. Then you configure the Rapid environment. Within what you will do is you will put the FMU, the FMI compliant model, the Modelica model, inside of a Simulink container that we just use for simulating the model and providing interaction, and then you perform optimization. And then you keep going like that until you reach your optimization criteria. I have a video that I can show you. I was showing everybody before. Okay, so this is a power plant from Bosnia, and they have done some tests to check the performance of the AVR. So we didn't have a model, so we created a model of the system, of a generator to an infinite bus, and we computed the steady state parameters by filtering the steady state of the measurements and computing the parameters. That's a pretty standard thing to do. And what we're going to do is that we want to validate the parameters of the exciter. We assume that we know the generator parameters. So we have a Modelica model, then we compile it into an FMU. We have the measurements, we put the FMU in a Simulink container, and then we work with Rapid to do the estimation process, which you can define entirely. So the software has been built with a plugin architecture, so you can define everything in the process, and you can change it because you have access to a source code. So it just goes through this process. The glue is provided there. This is the Modelica model of the system. Here you have the generator. This is the salient pole generator and static excitation system. And we will introduce the step change at the same point where it was introduced during the test. If you have the input measurements, you can just play them into the model also. This is the Simulink model where you upload the Modelica model in here. This has been compiled. Here you load the measurements that are just going to be used to display the output of the simulation coming from there and the reference data that you have. And then you go and you configure the environment through the graphical interface, but I don't like graphical interfaces, so actually the graphical interface has limited functionality. Everything is to be done with scripts in reality. So everything works from the command line. This is what's just done because the European Commission wants to see demos. So here you can see, oh, you didn't see that, but that's very nice because now here you can set up the kind of solver that you want. So you're gonna actually, we took the Modelica model and put it into Simulink, and we will use the Simulink solvers, ODE45. So any solver that you have, for example, if you wanted to use the sundial solver from the guys here from, it's a national lab, you could just interface it. You call it from MATLAB and you use that one. So that's pretty neat, I think. Then you set up the output that you want to compare and the parameters that you want to estimate here. So it's completely flexible. It could be a mechanical system, what we were doing. So then you set up the model, so telling him where is the path where you have placed different things. That's not that interesting, but you have to do some bookkeeping. And then you use whatever optimization method. So we have plugged in, we have a couple of native methods that we did ourselves, very simple ones. But actually you can use the MATLAB optimization toolbox methods if you have license of MATLAB or whatever. We have the Google particle swarm optimization method because you just download it and then you can plug it in. So I'm completely agnostic to it. It's a little bit hard to see here, but you see at each simulation you're calibrating the parameters. And if I take this over here, in the background you can see some numbers being updated. Those are the new parameters that you have. But if you're interested and come back later, we can try to do it together.
So can you also estimate limit functions in this?
Yeah, because it's non-linear. It's based on the simulation. As long as you have the measurements hidden the limit.
I see.
Because you cannot estimate what you cannot observe, the first rule of identification.
Because in the plot you showed for the 1996 blackout, the excitation limiters were completely off. That was one of the major problems in not predicting that problem.
Perhaps, I mean, in that case, you could build a different tool, one that checks that all of the data in your database is actually valid. So that could be some cleaning. We did, Tractable Engineering did something like that in our project. So it's just, you could do some standard tests to see if all the parameters are within anything known.
So many of the commercial stability packages now have that.
Yeah.
They kind of give you a warning that you
had to force
data
them.
is out of kilter in the sense that it does not fall in the normal range.
Yeah. Actually, the sim standard makes you put that information in, so you can't get away from it. This is also available on GitHub, so you can just go and get it. You do need some requirements for the installation, but just try it out. I show you the video demo. Okay, I don't have so much time, but I will just go very quickly.
You can show it to them in the afternoon.
Okay, so should stop now? Give me 2 minutes. We have worked a lot on synchrophasors. I didn't make that the main topic of my presentation because I've talked about it so much. So we have developed, I don't know, a lot of applications. This is one that we have in Norway with the control center where it's the power system. They can monitor it. Some iPad, iPhone stuff, force oscillation detections, interaction, the oscillations, voltage control. We have developed some tools for implementing these applications. So this is dealing with the communication protocols and reading data in real time, making it available to the user. We have implemented control prototypes. This is a damping controller that we have implemented. I will give you the slides. This is active load controller based on for damping. So it's all have been implemented. Have worked a lot of protection work on anti-islanding and GPS malfunction or hacking. Testing Synchrophasor implementation into SCADA. We did some